I'll time myself as well, just in case I tend to waffle. Okay, so yeah, so my name is Adam Milsom. I'm a postdoctoral researcher at the University of Birmingham. And I'm going to talk to you about what I did during my PhD, specifically using the CLF to study a levitated cooking aerosol proxy. So this was work with Andy as well. So Andy will know a bit about this. So first of all, I'll talk about the people, because without these people, this wouldn't have been possible. So I'm in the lab of Christian Frang at the University of Birmingham, and I was co-supervised by Adam Squires at the University of Bath, and funded by NERC. And most of my experiments were a collaboration between the CLF and Diamond. So we did X-ray experiments at Diamond with a simultaneous laser technique, which I'll go into a bit later. And I've highlighted some people here who've contributed to it. In particular, people at Diamond, so Nick Terrell and Tim Snow, and then Andy, who's on the call, who just talked to us. And actually Max Skoda at ISIS, that's another facility next door to the CLF. So it's all kind of in the same area. So I'll jump into what I was interested in. So I was interested in aerosols in the atmosphere and a proxy for them. So aerosols, or particulate matter, they're emitted either directly into the atmosphere from different environments. So either they're directly emitted, or they're formed by secondary processes, such as the condensation of volatile organic compounds, so VOCs, or at least the reaction products of those reacting with things in the atmosphere. So you end up with an aerosol sample, and this aerosol can go on to form a cloud droplet via the condensation of water around them. It can be transported, and it can do its thing by interacting with the sun's radiation. So it could scatter some radiation and have a climatic effect directly or indirectly by the formation of clouds, and clouds themselves can interact with radiation. And in terms of like the air quality aspect, particulate matter, in particular PM2.5, is important in terms of air quality. You don't always have nice molecules in your aerosol sample. There'll be things in there that might affect your health. And so it's important to know, to understand what's going on with aerosols, what might affect their processing in the atmosphere, both in the urban atmosphere and in any other kind of atmosphere you'll find on Earth. So that's kind of the motivation. And now I'm going to zoom into what exactly I did. So oleic acid is a molecule which is a surfactant. It's a cooking emission. And in this box up here, there's a person cooking his burger, and you're releasing a lot of organic molecules as a result. And some of those, or quite a lot of them, will be fatty acids. And so oleic acid is a fatty acid. And so the surfactant part of oleic acid, when I talk about surfactant, it's a molecule with a hydrophilic head, so something that likes water, and then a hydrophobic tail, so something that doesn't like water, which makes it surface active. And importantly, for the laser-based technique, we've got this double bond in the middle. So this carbon-carbon double bond, and things like ozone like double bonds. And with this Raman spectroscopy technique we used, you can follow this double bond signal as it reacts with ozone, and then you can get chemical kinetics. So how fast does the reaction happen? And the question is, oleic acid lasts longer in the atmosphere than predicted in the lab. So that's an observation in the literature. And the question is, why? Why is that? And one of the sort of explanations for this, or a proposed sort of hypothesis, is this self-assembly. So as a surfactant molecule, oleic acid can form these three-dimensional nanostructures. And what's interesting is each of these nanostructures has different properties. So some of them are very viscous. Some of them are opaque, some of them are translucent. So that means they're interacting with light differently. And this could be a possible explanation for this lengthening of this lifetime of oleic acid in the atmosphere. And this can be related to air quality and that kind of thing. So next slide. So what did we do? We levitated droplets of this proxy, of this oleic acid, actually mixed with its sodium salt, sodium oleate proxy. And we did simultaneous small angle X-ray scattering, or SAX. So this was the stuff at Diamond. And the SAX gives us what kind of nanostructure we have in the particle. And then at the same time, we're using Raman spectroscopy. So this is the stuff from the CLF. and we can use that to measure the reaction kinetics when we expose these droplets to ozone. So that's sort of a summary of that technique, and here's a schematic of that. This is from a paper that from my supervisor, Christian Frang, before I came along. And yeah, so we levitated using sound, so acoustic levitation. We shoot X-rays at the particle to get this SAX data. And at the same time, we poked a Raman probe in there and pointed it at the particle or at the droplet, and did some simultaneous Raman. And we can control this gas phase environment. So we can change humidity, we can expose the stuff to ozone. And that's what we did. And here's a picture of a levitated particle, and we took vertical X-ray pictures over time at the same time as doing the Raman laser technique. So, you know, why the CLF? Why was that important in this study? So this is something we published quite recently. And we had ozone in oleic acid in a crystalline form. And we compared the reaction of that. So remember, we're looking at this double bond, and this plot here is the decrease in that double bond signal over time. So we're looking at basically the decrease in the amount of oleic acid over time. So reaction kinetics. And this crystalline form, so these triangles, this decays much slower than for the liquid forms, so these blue circles. And so there's an effect of this phase. So the crystalline form of oleic acid reacts a lot slower than the liquid form. Sort of makes sense because things diffuse through solid media much slower than they would with liquid media. And here, so on the right-hand side, this is X-ray based stuff. All I want you to know is this is a vertical scan through the droplet. So we're looking at the top, the left-hand column here, and this strong sort of peak is a peak for crystallinity. And over time, as we go down this plot, this is as we're exposing the stuff to ozone, this crystallinity decreases over time. Eventually, it's gone. So this is after about 400 minutes of reaction. If we just believe the X-rays, we would think all of the oleic acid's gone. But if we look back at the Raman data, so this kinetic decay, this is from the same experiment, there's still quite a strong peak for this double bond existing in the particle. And so this simultaneous technique has allowed us to say, well, actually, oleic acid is still in the particle, but it's not self-assembled. Because we would think, oh, once it's gone, once the self-assembly is gone, that means the oleic acid's gone. So that's quite interesting. There's also evidence here for some sort of aggregate forming from the X-ray data, but that's kind of another conclusion. So I'll sort of go through the implications of this. So it means that this crystalline phase significantly increases the lifetime of oleic acid. And remember, right at the beginning, we said oleic acid seems to last longer in the atmosphere. So, you know, this could be a possible explanation. I'm not suggesting there are particles of pure crystalline oleic acid floating around, but if there's some of it, that could be a potential explanation. Possible crust forming, as I mentioned, and this is sort of the first experimental evidence of an aggregate forming. And even after the loss of crystallinity, there's still some oleic acid left, and that's what this laser technique helped us. Helped us come to that conclusion. And is there a longer lifetime for particle contents? That's sort of a question I put in, or sort of speculated at the end of that paper. And yeah, so this simultaneous technique was very useful in sort of determining these conclusions. And there's more work to come, hopefully soon. But yeah, so this is kind of the application of, or my application of using the CLF for this sort of air quality or atmospheric aerosol research. So here's a list of references. I think this is all recorded, so you'd have to jot all this down right now. But if you want to contact me, here are my details at the bottom. That's my Twitter, that's my email. And yeah, I'll stop there. I think we'll do questions afterwards, but yeah, thanks for listening.